that I broke this up as I described in my last video is to give me more time to spend on particular systems. And today what I'm going to be talking to you about is the power supply. And the best place to start is the linchpin of any kind of a high energy pulsed deposition discharge system, and that's the capacitor. The capacitor in this laser is an unusual capacitor, and if purchased new would cost about $12,000. The reason it's so specialized is because in order to produce the highest speed, highest energy pulses, you need a specific capacitor called a discharge capacitor. Discharge capacitors are unusual in that they have a very low self-inductance. The lower the inductance, the faster the capacitor can output its energy. And for energy discharge or flash lamps, you really don't want capacitors that have an inherent inductance greater than about 1 microhenry. In the very best ones, they get down in the tens of nanohenries, and that's important for high speed. In addition, you want a very high voltage capacitor because based on the LC circuit design of any kind of a discharge system, you're going to have a floor of how low you can get the self-inductance or the inductance of the system. Mechanically, you're just limited to that. So by discharging the same amount of energy in a higher voltage, but with a lower capacitance, you increase the speed of the discharge. So low inductance, high voltage, and specifically discharge capacitors are made for the purposes of very rapid loss of voltage, very rapid discharge mechanical forces. Because when you charge up the capacitor, you compress the plates against each other and you produce a lot of potential energy. When that energy is discharged in a couple of microseconds, the plates expand away from each other and create a shock wave. That shock wave, repeated a couple of times in regular capacitors, will begin to tear apart the internal leads of the capacitor. They can squeeze the electrolyte that's between them or the insulator, the dielectric. And so very quickly they will destroy themselves if they're not built to do discharge. So to get a very special capacitor like that, you're almost certainly going to have to find it surplus. And you can. A lot of national labs will part these things out after a certain lifetime, even if they're quite good. And you can get capacitors like this for a few $100s, but you have to shop. And it's important whenever you're going to buy something that's going to be a determinant for everything that goes upstream and everything that comes downstream, you're going to need to make sure that that system, if it breaks or becomes unusable, you can replace it. So it's a good idea when you buy those to buy more than one. I was lucky I was able to buy a whole pallet of 4 of these. And as you see on the other side of this room, these are 3 identical capacitors to the one on the laser. And this is behind my other little project here, so don't trip. The capacitor, as you can see, is a 22,000 volt, 100 microfarad with a self-inductance of 40 nanohenries. So it's an excellent capacitor, and it turns out all of them are good. So I've got a nice stock of backup. But one of the things that you're going to then have to do is once you've established what kind of capacitor you're going to use, you then have to decide how you're going to charge the capacitor. You've got 2 choices. You can use a switching power supply, a high energy switching power supply that would be capable of, say, as much as 20 kilovolts and a few kilowatts. It's going to be almost impossible to find that. You're almost certainly going to have to get that as a custom product. And as a result, I elected, and you probably would too, to use a simple inductive line frequency inductive system, high voltage transformers. And so that's what I'm going to show you down here. The 2 transformers here are called ABB transformers. They're sort of outdoor rated, very robust transformers. These particular ones are rated at 120 to 1 step-up ratio and 1.5 kilowatts each. So you can obtain them from anywhere from about maybe 300 watts up to about 2 kilowatts. And in this application, I'm using 2 of these in parallel. And they're running on 1/2 of the 230 volt circuit. So essentially they're running on 120 volts. They have an RMS output of about 14,000 volts and a maximum achievable charge voltage into the capacitor of about 19,000 volts. The question though is going to be, how do you control the charge level that you want to reach for your capacitor? And you've got 2 choices there too. You can either use a variac, which is an auto transformer that varies the line voltage into them. That's one way to do it. And this 10 kilowatt rated variac and these 2, so therefore 3 kilowatt transformers have a little bit of a problem with resonance because of the almost dead short nature of a large capacitor charging. When you go over about 1 kilowatt of charging energy, the system begins to vibrate and resonate a lot. And it's difficult to tune that out because there's some variables in the system that are hard to control. So what I decided to do, which turns out to be actually a much better solution because it doesn't require the bulky, expensive variac, is to control the ultimate charging voltage by controlling the charging time. So if you come around to the other side of the laser, what I did is I took the variac out and I replaced it with a high power mechanical relay. Each side is rated at 40 amps and I'm running both sides so I can put up to 80 amps through there. And it's a 12 volt coil that is controlled by a timing circuit. And the timer, inexpensive and pretty reliable, has a resolution of 10 milliseconds. So I can control the charge voltage across the capacitor with incremental increases in the charge duration. And the ability to control with this particular unit is about 0.1%. I can control the voltage to about 1 part in 1,000, and it's repeatable to 1 part in 1,000. So this system actually works a lot better than the variac system and allows me to control the voltage easily by just adjusting the time. However, it is a little empirical. I mean, you have to figure out what time is going to reach what voltage, but once you've established that, it's a set factor and you know exactly what you're going to get each time you charge the laser. You still have a problem though when you charge the transformers from the line. The transformers are charging what looks to them initially almost like a dead short. And so they would draw 30 plus amps each from the line, blow the circuits, potentially overload themselves. And so what you have to decide how to do is to limit the initial charging current, either by using a large resistance. I used a couple of these 2 ohm resistors, which provided good current limiting, but it's a very inefficient system. Just like the plumbing example, like when you want to resist flow through a tube, you do it through an orifice, but there's a lot of resistive loss in that kind of a system. A better method of doing that is with a surplus microwave oven transformer. This is a 20-to-1 step-up high voltage transformer, but when you take the 2 high potential leads, essentially the high voltage coil, and you short it out, you effectively remove it from the system. You could literally pull it out of here because it does nothing. You now have a line voltage inductive coil with a great big block that will oppose the current flow in the initial stages of charging by, in the plumbing analogy, causing the voltage or the fluid to go uphill to a container. And so you don't lose any energy because the energy is stored in that field of the inductor, and consequently as the voltage potential goes down on the across the transformer as the capacitor is charging, what happens is the energy that had been stored in the inductor then ends up re-entering the circuit and being put into the capacitor as well. Consequently, this system warms up very little. It's very efficient, and one of the very nice features of using these as your inductors is that they're cheap. You can get this for about $7 on eBay. And rather than having to carefully design a very specific inductor that's sized to the loads that you're producing, if you get several of these things, you can use them either in series or in parallel to adjust your inductance. So if you run the line in one side, out the other side of your transformer, you've got one inductor. If you run them in parallel, in series, you double the inductive impedance, and as a consequence lower the charging rate by a factor of 2. If you put them in parallel and run the power in and out to your transformer, you decrease your inductive impedance by a factor of 2. And so with as few as 3 of these, you could vary the current rate or the charging rate by a factor of 10. And it's very inexpensive, it's very convenient. And it turns out I was lucky. My system works very well with just a single inductor. So as you can see, between the 2 ABB transformers, I have 2 of these, but simply because each one is feeding each transformer. And so as a result, I end up having 2 inductors, 2 transformers into the high voltage rectifier, which is a full wave rectifier over here, high current, high voltage rectifier, that feeds the capacitor. You might want to bring the camera over here so you can get a better view of what I'm going to show underneath here. If you look underneath from this angle here, and you look way up underneath here, you'll see the 2 big posts that come out of the capacitor, the high voltage post and the ground post at the other end. As a note, this is a isolated ground case, so there's no potential, theoretically, there should be no potential on the case. Nevertheless, I don't trust plywood, so I put it on an insulator. Back to the point. You see on these posts are 2 large plates that have been bolted to them. And the large plates, because of their size, reduce the inductance of the current that flows into the head up above. But they also provide nice, convenient places for me to attach additional leads, because I can just drill and tap a hole wherever it's useful. And so you'll see the power that comes out of the rectifiers into this high voltage side here. You'll also see a resistor stack here that acts as a voltage divider. So these 2 30,000 volt resistors have 1,000 times the resistance of the lower voltage resistor right over here. And so as a result, the voltage potential from this point to the ground is 1,000 times less than the voltage potential from ground to this end over here. I use the 2 resistors simply because if one of them failed, I still can hold off the full potential here, and just a safety issue. If you look even further up underneath here, you have to look up, you'll see attached to the plate 2 posts that stick up through the fiberglass. They go to the head. I'll show you what they do in just a second. But if you then look right in front of the first post, you'll see a lead coming off of there and coming down to this fiberglass plate over here. Underneath this plate, again, you're going to have to look underneath there, you'll see a stack. You'll see a stack of 20 high voltage, high power resistors that are operating in series and act as a dump resistor. The reason that is a critical component with any kind of a large capacitor like this, it's not something you get around to at some point. You have to do this right from the beginning. The very first time you charge this capacitor, you have to have a system like this, because you can't crowbar a resistor like this to make it safe. This capacitor is so far beyond lethal that not only would you electrocute yourself if you touch this high voltage post, you'd blow your hand clear off. There's so much energy in there. So crowbarring this is just not possible. It's also very damaging to the capacitor because you produce a very high mechanical loading that rings back and forth between the two posts, back and forth. The voltage will invert and it will ring down over 10 or 20 cycles, and you'll damage the capacitor very quickly with a crowbarring. So the resistor stack that you see that acts as a dump is connected to a relay here. And this relay, as you can see right here, is normally closed. You have to activate the coil in order to open it up and make it possible to charge the capacitor. The reason for this position is that if the power is off to the laser, or I hit the dump switch to the laser, or I hit the mechanical switch, power loss to here will mean that this thing will close and it will make the capacitor safe. That's the best way to do this with this high voltage relay. And you'll also see that if I open this up, it has to give a very large spacing here because the full potential of the laser is across this switch right here, and that's why that has to be a very specialized type of switch. If you then come up, and let's take a look at what you see on the top here. The power that comes from the high voltage part of the capacitor feeds through this thin strip to this large aluminum vessel. It's a containment vessel for the explosions that could occur, but it's also a coaxial conductor. The electrical energy travels down and around the flash lamp to this end. It attaches at the end of this conductor through this little copper strip to this vertical plate. And so as a result of that, you end up with a coaxial current path, and the coaxial current path has much less inductance than, say, if I was to just take a flat strip and travel all the way along here to this end and connect it to the high voltage end of the flash lamp. The inductance is about half overall inductance is about half of what it would be by using a coaxial conductor. It would be even better if this coaxial outer part were tighter, smaller, and closer to the diameter of the flash lamp discharge, because the field that's limited within there is what determines the inductance of a coaxial conductor. However, for convenience sake, I left this somewhat larger because the extra added inductance is relatively small compared to the fact that I'm using a coaxial system at all. And that allows me to place inside there, which you'll see better when I take this off in a subsequent video, the reflective chamber that contains the light and the dye cell. That chamber is then independent of this, and I can manipulate it and size it and fabricate it without having to take any concern about how I'm going to wire it up. So finally, what happens then is that the power that goes down through the ground will go down through this other plate here and eventually down to the capacitor. If you look over here, rather than me try to take this apart right now, I'll show you some examples of the flash lamps that I've used in some of the earlier versions of this, but they're pretty much identical in their design, so it'll give you an idea what's going on in there. At one point, I was actually using xenon-filled, commercially made, custom-made flash lamps. One person complained about the fact that I was pushing or I was promoting certain manufacturers. I'm not. But whenever I find a good one, I'm happy to give them some recognition as well as give you a source. This came from a company called Phoenix, F-E-N-I-X, and they make very low cost, very high quality custom flash lamps. And it'd be a good place to check out if you're looking to build something like this and you want to use sealed xenon. This same flash lamp is actually mounted in this cooling arrangement here. And this is an example of the current type of system I'm using, which is an ablative wall flash lamp. This system has to be filled and emptied. This system obviously doesn't. That's why you don't have to have any gas feed in here, and that's one of the big advantages of the xenon system. In addition, if you're running at lower energies than I run, the xenon is more efficient because it's a line emitter. It's not just a thermal emitter, and so as a consequence you get more power at lower energies. But once you start to get to the higher energies, these become more efficient and more useful for the dye laser. The question then is how you trigger it. As I've said in the earlier video, I used a Thyrotron. And this is a little bit smaller. A Thyrotron produces a very nice switching method and has very low self-inductance. But they're bulky, they're expensive, they're bulky too. And so as a consequence, even though they themselves don't have a lot of inductance, they require a lot of additional lead length, which adds to the overall inductance of the system and slows down the flash lamp pulse. When you get to 30 or 40 kiloamps, as I am right now, the Thyrotrons become enormous, both in cost and in size, and it just becomes prohibitive for this kind of a system. I built, at one stage, a pressurized spark gap, which can handle those kinds of currents, and is smaller, and therefore a little bit less induction generating. But nevertheless, it still was not as good as using the flash lamp itself as the switch. So in one application, I wrapped wire around here and used a high voltage trigger to trigger the pulse. But one of the problems with that kind of triggering is that the wire, wherever it lays, tends to induce the current to run hotter at that location and causes some degradation and solarization of the tube. They wear out a little quicker. Another method that I used, and actually it's a very good method, is injection triggering, where when I was using two flash lamps at one point, high voltage in to this end and ground out to this end, and the two other ends were attached across each other and were essentially floating. And then by placing a high voltage pulse into the floating lead, it would discharge one of the tubes, causing the overall hold-off voltage of the system to drop below the charging voltage, and it would discharge. It works very well, and it doesn't induce any additional inductance. But when you go to a single tube, that's no longer practical. And so therefore I went to the system that I'm using now, which is based on a switch that's similar to this early version for testing purposes. Effectively, this tube here is hooked up to the end of the flash lamp, and high pressure gas flows in here, vacuum over here. And by using these solenoids in an alternating method, I can fill and then dump, fill and then dump by using the two switches in an alternating method. If you look here too, you'll see this is how I support the flash lamp. These plates of aluminum are bored out better probably seen over here, are bored out to slip fit the posts that come out of the lamp. And then a slice is made here to allow you to clamp this down and produce a very nice squeeze of the end post. Gives you very good thermal and electrical contact. And because of this very large aluminum, highly conductive plate with a lot of cooling holes in it, it gives you the ability to keep the electrode cool as well as support the electrode in a certain position. Also, as I've said in earlier videos, I use this silicone to float the cooling tube over the lamp, and in the case of my homemade lamps, float the electrode within the lamp. And so as a result, this prevents any kind of point loading or torsion on the tubes when they are firing and shaking a little bit, or when they are clamped down. If things aren't perfectly straight, you can see these things wiggle a little bit. And that little wiggle provides a lot of protection against misalignment. If you come around here, the gas system that goes into the tube comes from this tank, which is an argon-helium mix. Argon produces about the best light output, but it's produced kind of unstable discharges. So by mixing a little bit of helium in here, it stabilizes the output but retains most of the benefits of the argon. At about 8 psi, this flows into this box here. And if you look here, you'll see at one point I had 6 flash lamps. I'm using just one now. There's a needle valve that controls the flow of the high pressure gas into the output line. And there is also a solenoid here that is a safety backup, because if I forget to open the argon and the vacuum pump continues to dump the tubes, eventually this entire system will become evacuated and no longer resists electricity. And effectively, there would be a potential way for this to become hazardous. So if the pressure goes down in this line or I forget to open it, this solenoid will close, effectively works like the dump switch, dumps the capacitor, turns off the power supply. It's a safety feature. And then I can adjust this with this little plastic standoff so I'm not touching the needle valve. Finally, last part of this is if you come back around here and take a look at the vacuum pump, you'll see an identical version of this switching system, solenoid system that I had over there before, but these are vacuum rated, high speed, high flow solenoids that work better than the original ones. And so the vacuum comes out here, the high pressure goes here, and from this T goes up to the flash lamp. The vacuum then comes into this ballast chamber. The reason for this is twofold. One is during the periodic dumping and filling, the vacuum pump continues to run and draws this down to a moderately high vacuum. So when the valve opens, the flow of gas out of here is very rapid because it doesn't depend on the real-time pumping rate of the vacuum pump. And so you get a much quicker discharge, or essentially a much quicker triggering. And then finally, if there was a catastrophic explosion that occurred, as I keep talking about in this video, then all the glass and the fluids and everything that might potentially get into the vacuum line will dump into that ballast or that chamber and not get into the vacuum pump. So it's a safety backup feature. So that's pretty much it for the electrical system here. And in the next video, what I'm going to do is I'll take off some more of these components. We'll dig deeper. I'll show you the pump chamber, how I made it, how you could make it, how I fabricated it and fitted it, as well as the optical system that's the core of what makes the laser actually operate. So I will see you again soon, and I hope you enjoyed this video.